Hello everyone, and welcome to our webinar introducing you to the Manipulative Kit that is designed to support the Foundations of Algebra course. My name is Sarah Delano Moore, and I'm the Director of Mathematics and Science at ETA Hand to Mind. We're the providers of the kit, and so glad that you're able to use these materials in your Foundations of Algebra course. I want to begin our session today by talking a little bit about why hands-on learning is so important and why the folks organizing the course chose to put together a manipulative kit to support it. And then we'll get into the specific manipulatives in the course and some examples of the kinds of activities you can do with those manipulatives to meet the standards that the course addresses. The use of hands-on learning is supported by a long history of research, and that really culminated in some ways with a 2013 recommendation from the National Council of Supervisors of Mathematics that the use of concrete and virtual manipulatives should be systematically integrated into classroom instruction at all grade levels. In the Foundations of Algebra course, you are likely working with students whose history of success in mathematics is slim. They are there because they are not yet ready for algebra, even though they might be of an age and grade where typically students would be. And so part of your role is to create a classroom environment that likely these students have not had before. And that includes the use of hands-on material and really building on this history of research to create the right kind of conceptual foundation for these students to begin to find success in mathematics. NCSM made this recommendation because of the history of research behind teaching with manipulatives. I'm going to highlight three pieces of that here. First is a report from the What Works Clearinghouse at the U.S. Department of Education, focusing on response to intervention in mathematics. And for many of you, your students in Foundations of Algebra really are intervention students. They are students who need additional strategies and support because their history has not given them the base they need. And this research review and recommendations for policy based on that research include the recommendation that systematically using visual representations and manipulatives can lead to statistically significant gains in achievement. Adding it up, a report of the National Research Council takes that idea a little bit further and says manipulatives provide valuable support when teachers interact over time with students to help them build connections between the objects, the symbols, and the mathematical ideas. Simply having manipulatives in your classroom or doing a hands-on activity and then returning to abstract symbolic practice over and over again is not going to make a difference. What does make a difference is building connections, and the model we typically use to build those connections is this one. The idea that we move from the concrete to the representational and then to the abstract. We build things, we work with hands-on objects. Then we sketch those representations visually. And then finally we connect those visual representations to the abstract. I'll be illustrating different aspects of this throughout the webinar today. I will not go all the way through the cycle each time, but you should think about how can I work all the way through all three pieces with each manipulative activity that you do. What happens? What's so powerful about this model? What happens to student achievement? Researchers asked that question as they analyzed NAEP, the National Assessment for Educational Progress. And what's interesting about NAEP is that not only do students take content assessments, solve these math problems, but they also complete surveys, both students and teachers. How often do you use calculators? How often do you have homework? How often do you use manipulatives? Questions about the kinds of experiences they have in math class. And so researchers looked at NAEP data for two groups of students. Those who reported using hands-on learning on a weekly basis, which I think of as an ordinary part of our classroom routine. It's a regular occurrence. And they compared them with students who reported using hands-on learning on a monthly basis. Manipulatives are a special event. They only happen once a month or so. The researchers found that those who use hands-on learning on a weekly basis scored almost 3/4 of a grade level ahead of students who were using hands-on learning on a monthly basis. It's these kinds of findings that really suggest that Making this an ordinary part of classroom routine is a very powerful tool and a very strong way to help students build connections when we use the manipulatives with fidelity, when we move from that concrete through visual representations to more abstract representations as part of the learning cycle. The transition to new standards has asked us to focus where the standards focus, to emphasize coherence in our instruction, and to build the rigor of our classes. Your Foundations of Algebra students have come through the upper elementary and middle grades in a time of transition from one set of standards to the next. So focus may not have been quite as crisp. The real coherence from those very early primary grades experiences in adding and subtracting all the way through middle grades work with algebraic expressions may not be tightly developed yet. And this idea of rigor as the balance across conceptual understanding, procedural fluency, and application may not have been fully settled in each of the mathematics classes they had before they came to you. Manipulatives can help you put these tools into action. By using manipulative models, we can illustrate the coherence of mathematical ideas. I'll show you an example of that, particularly around multiplication. And the use of manipulatives in particular is focused on this idea of conceptual understanding. Students need to be fluent in procedures. They need to know their multiplication facts and how to multiply two-digit numbers. But they need to do that from a position of sense-making. I understand what's going on and what's represented by these numbers, not simply memorizing a procedure and then applying it blindly at opportunities where they think it might fit. Manipulatives help make this happen. They give students tools for seeing conceptually what's going on and for building procedural fluency from that. The third element that's important is application. And you'll see that here in that our use of manipulatives will often be grounded in a simple real-world example or real-world problem that gives some context to the mathematics. When we teach with manipulatives, we get a number of benefits. The first is student learning and achievement when we use them well. The second is that our standards for mathematical practice, that notion of how do we do mathematics, is really fully integrated. Using manipulatives helps students persevere in problem solving. It gives them strategies, things to do when they're not sure what to do. Using manipulatives helps students with mathematical modeling, and manipulatives serve as tools in mathematics. The repetitive steps one might follow in working with manipulatives help students understand the regularity that's part of computation in mathematics. These kinds of examples show you how the standards for mathematical practice become illustrated and really highlighted through the use of manipulative-based instruction. We show how mathematics concepts are taught consistently, have a common meaning across multiple dimensions, multiple kinds of numbers. As I said earlier, I'll show you a multiplication example of that, but it's true across any number of aspects of mathematics. And then fourth, by working with manipulatives, students are really reasoning about the mathematics, and that develops critical problem solving and strategic thinking skills that allows students to really get invested in making the mathematics make sense. And ultimately, that's your goal in a course like this. You have students who are likely reluctant about mathematics because their history is not one of success. And the more you can say to them, I believe this course should be about everything you do in mathematics making sense, and we're going to use these manipulative tools, we're going to use these new strategies to help make that happen for you, is really a critical part of your success in teaching this course and in building good relationships with the students that you have. A few tips for getting started. One is to introduce new models by showing how they can represent mathematical ideas. You'll see a number of examples of that from me in today's webinar because that's really what I'm doing for you in this setting. Your students as adolescents are able to think about how can I use this to represent multiplication? In the primary grades, we're often not as explicit about the mathematical connections in our first stage of exposure. We tend there to have our initial exposure be play. Explore these things. What do you notice? And I highly recommend that to you as a strategy as well. Give your students a few minutes to explore. What do they wonder? What do they notice? Who can build the tallest tower? Let's take a look and get to know these new tools, and then begin to see what mathematics they can help us with. Second, most of the time you want to allow your students to choose freely from the different models that are available when they solve problems. Think about how your classroom is organized. Can you have manipulatives out and available to students so that if someone wants to use a particular tool, they can grab it and go? They don't need to raise their hand and ask permission. It's not terribly disruptive to the rest of the class. It's fine to quietly get up and walk over to a bookshelf and grab a bin of base 10 blocks or another tool. I don't want to have to open 4 bins and pour things out, because that noise and activity will begin to be disruptive. If students are seated at tables or in groups and they can have manipulatives in a bin or a basket right there at their workstation, that's even better. Third, when you see students having trouble, encourage them to use the models. If you see a student struggling with a problem, have you thought about how Cuisenaire Rods might help you? Have you thought about which manipulative tools could help you model this problem? Which things have you tried? By doing that, and by treating manipulatives as a routine mathematical tool, you're conveying to students that this is an important tool, and it's something we use because it has value. It's not a baby tool that I've brought up to this upper level to punish you. It's a different way of approaching mathematics to help the mathematics that you do make sense. I, as a teacher, value it, and I encourage and really expect you as my student to value it as well. These suggestions come from the course overview document for the Foundations of Algebra course, and I think they're really excellent suggestions in how to get started. We'll move now to the manipulatives in your kit. And at this point, I want to encourage you, as you watch this webinar, to make liberal use of your pause button. I'm going to go through here the different manipulatives with a picture. Mine may be a slightly different color or, or configuration than you have in your kit. But take a moment and pause as you need to find the particular tools that I'm talking about, so that as we get into examples, you know what you have. When we work examples, I'll encourage you again to pause, because I want you to take the manipulatives out and try the activity. Think about what this would be like and how you might approach it before coming back to listen to how I describe and explain it. The first manipulative you have is base 10 materials, base 10 blocks. You particularly have the small unit cubes, 1 centimeter on a side, the 1 by 10 centimeter rods, and the 10 by 10 centimeter flats. There's also a larger 10 by 10 by 10 centimeter cube that is not part of the kits you have, but is sometimes included in a set of base 10 blocks. You have decimal mods. These are a small, flat blue piece of plastic. This picture is not to scale, that represents 1/10 of that small unit cube in your base 10 set. You have a factor track, a plastic L-shaped track that the base 10 blocks fit into, and that we'll use when we talk about multiplication in base 10. You have place value chips, small, about 1 inch across, foam chips. Each place value is a different color, and each chip is labeled with its place value, 1, 10, 100, 1,000. These can be used to represent numbers in various places, and we'll talk about them a little bit for adding decimals, I believe. You have fraction tower equivalency cubes. You'll notice that each full tower is the same length, and the pieces are labeled with fractions, with decimals, and with percents, and then the fourth side is blank. The towers snap together so that I can build fractional representations, and you have along with that a set of fraction number lines that are keyed to the same unit length as in your fraction tower cubes. You have a set of Cuisenaire rods. This colorful staircase is a manipulative of long standing, more than 80 years old at this point, and a really powerful tool, in our case, particularly for studying ratio and proportion and modeling the idea of unit rate. You have an XY coordinate pegboard, a 15 by 15 grid of holes, a set of axes that slide on them, and pegs to both anchor the axes and mark points, along with some geobands that you can use to indicate the shape that you've created or the line that you've drawn. Yours are probably wrapped in a white cardboard sleeve that says XY coordinate pegboard on the front, but you can see the yellow on the side as you look at that sleeve. You have a set of AngLegs, plastic strips in different colors with a little button connector on the end, and protractors that can be used to measure angles. We'll look at those for thinking about similar triangles and ideas of slope. And then you have a set of Algeblocks. I have the blocks here, and they come in addition to the blocks. There is a set of mats. We'll work with a couple of those mats in our work today. And there is a 4-quadrant factor track. It has grooves like your base 10 factor track, but it's shaped like a plus and resembles the 2 coordinate axes that define the coordinate plane. And again, we'll look at examples of how to use these. So these are the manipulatives in your kit. Feel free to take a moment now and get organized, make sure you can find everything. Again, pause and rewind are your friends. And we'll move on to thinking about how can we use these to model different ideas of mathematics. We're going to start with number sense and quantity and standards related to this topic. And we're going to begin by thinking about the powers of 10 using your base 10 blocks and using decimal mods. I'm going to ask you first just to think about the relationships among the different pieces. And I'm going to switch to Active Inspire, which is a virtual manipulative representation of what we're working on today so that you can see what the manipulatives look like. My base 10 materials are green. Yours, I believe, are blue, but color doesn't matter. I'm starting here with the large 10 by 10 by 10 centimeter cube that typically when we use base 10 materials with young students represents 1,000 because that's its volume, 1,000 cubic units. And the question I want to ask you to think about is, what if I separate this cube into 10 equal layers? Can you look at your base 10 materials and identify the shape that you think you'll get if you take this large cube and separate it into 10 equal layers? I hope you identified the flat, the 10 by 10 by 1 centimeter, if I continue to define it by volume piece. If I take that and think, what if I divide that into 10 separate units? 10 equal columns, what would I get? I'm going to get the long or the rod. And if I separate that into 10 equal cubes, notice I'm back to my cube shape, and I call this piece the unit. The first thing I want you to think about here is the name I've given the pieces. To emphasize the ones you have a flat, you have a long or a rod, and you have a unit. It's very important that you separate the name of the piece from the value that it has, because we're going to talk about how to use these to represent decimals. And when we represent decimals, I might use a piece, I'm likely to use a piece other than the unit as 1. So one challenge your students may face is that they think of the unit as 1, and they in fact call it a 1. They call the long a 10. They call the flat 100. You want to get them back to thinking about the names of the pieces and then defining its value. I've asked you one last question here. What if I take that unit, that small cube that you have, and separate it into 10 equal layers, just like I did with my large cube the first time? What you'll get at that point is the decimal mod, or what I sometimes call the mini flat. 10 of those stacked together will be the size of your unit. I can imagine taking that mini flat and a very tiny pair of scissors and slicing it into 10 equal columns. You'd have mini longs or mini rods. I could slice those even further. It becomes a mental exercise because the pieces are too small to be practical. But I want students to think about this because this emphasizes the power of 10 relationship among the different place values. Each of these physical pieces represents a different place value column, represents a different place value. And I think about that, I define the particular number by looking at which piece represents 1. So I'm going to model a game for you, and I'd like for you to gather these base 10 pieces together. Remember to use your pause button and freeze the screen right here while you find your pieces. This is not a race. You'll need 1 flat, 2 rods, 3 units, and 1 mini flat. Once you have those pieces together, here's your question. If this collection of blocks has a value of 1 and 231 thousandths, which base 10 piece has a value of 1? Is it the mini flat that has a value of 1? The cubes, the units that have a value of 1? The rods, do they have a value of 1 in this setting? Or the flat, does it have a value of 1? If this collection represents 1 and 231 thousandths, take a moment and think about which piece has a value of 1 and how would you explain that? I might think about this by saying that decimal mod, that mini flat, is the smallest piece I've got, and 1,000th is the smallest portion of my number. So these units are 10 times bigger. They each represent a hundredth, and I have 3 of those. These rods are 10 times bigger. They each represent a tenth, and I have 2 of those. And this flat is 10 times bigger. It represents my unit. It has a value of 1. I could do the same reasoning by going in reverse. Each piece gets 10 times smaller. This is what's called a proportional model for base 10 materials, and it's really helpful for students reasoning about what's going on. Now let's think about the same group of materials, but in a different way. This time, the value is 12 and 31 hundredths. What's 1? 1/100th might be my mini flat. 3/10ths my units. 2 rods, my ones, and 1 flat, my 10. Students might also think here about, well, there's a 2 in the ones place, and the only shape I have 2 of is that rod. So as you craft examples, you want to give students opportunities where sometimes there's a 1 or whatever the ones digit is in more than one place, like my first example, and other times like this one, where that simple reasoning about place value gives them a hint, and then you can ask them to expand on that idea more mathematically. Take a moment if you'd like, and if you're with a partner, each of you build a collection of pieces, give it a value, and trade. What's 1? See if you can figure it out. We've looked here with powers of 10 at the patterns we see when we work with whole numbers and decimals. The idea of moving the decimal point back and forth, left and right, as representing multiplying or dividing by 10, because the scale of my pieces goes up or down by a factor of 10. And base 10 blocks are a very powerful tool, particularly joined with the decimal mod mini flat, to help make that happen. The second exploration we're going to do today is working with fractions. You're going to use your fraction equivalency towers, and you're going to use your fraction number lines. I encourage you to pause for a moment now while you put your base 10 materials away and get your fraction materials out. Once you have your fraction materials available to you, we're going to look at 3 topics around working with fractions. We're going to look at naming fractions in terms of unit fractions. We're going to look at different strategies for comparing fractions based on reasoning about fractions and conceptual understanding of what a fraction is. And then we're going to look computationally at how do we explain division of fractions? How do we reason about dividing fractions so that students know what's going on there and can see the connection between dividing fractions and dividing whole numbers. I'm going to switch back to my virtual manipulatives, and while I do that, I want you to make sure you have your materials in front of you. I'm using here the fraction number line that looks like a ruler. It is partitioned in that way. And you can see I've taken the red unit tower, the red one whole, to show that this defines the space from 0 to 1. Let me go ahead and put that label on our number line as we go so that we can see. This point is 0 and this point is 1. The yellow piece that I have here is a 1/4. And my definition of fractions tells me that 1/4 is what I get when I divide one whole into 4 equal pieces. One of the things we want students to understand about fractions is that they really are numbers. And so one of the things we can do with numbers is we can count, and I can count with fractional pieces as well. 1/4. Take a second one and move it over. That's 2/4. You can follow along by simply adding another one of the 1/4 pieces from your set. There's 3/4. Here comes 4/4. Now this is where I have a virtual advantage. If you're with a partner, pool your resources. Here's 5/4. Here's 6/4. Here's 7/4. And I could keep going. You'll notice that I did not say 1/4, 1/2, 3/4, 1, 1 and 1/4, 1 and 1/2, because I wanted to emphasize that I'm counting by these 1/4 pieces. One piece 1/4 in size, 2 pieces, each 1/4 in size, 3 pieces, each 1/4 in size, 4 pieces, each 1/4 in size, 5 pieces, each 1/4 in size. I can regroup just like I worked with base 10 blocks with whole numbers, because I can say that those 4 1/4, those 4/4 together, can be renamed as 1. But fundamentally what I'm doing here is I'm counting. And as students have experiences, what's the size of the piece when you divide the whole into 4 equal parts? What's the size of the piece when you divide the whole into 5 equal parts, into 10 equal parts, into 2 equal parts? They begin to see that the more pieces you have, the more pieces you've divided that whole into, the smaller each piece is. You see that in your kit because the black 1/12 pieces are much smaller than the pink 1/2 pieces. That makes sense. It takes 12 of those black 1/12 to make a rod the length of 1. It only takes 2 of the pink 1/2 pieces to make a rod the length of your 1. Feel free to pause for a moment and explore that idea if you'd like. I'm going to move now to some comparison problems where I'm asking you to build models and reason about fractions to compare and always to find which of the two fractions I've given you is greater. Here I'm using the double number line from your kit. And again, I can think about my labels. I'll write them in the middle this time. This spot is 0. This spot is 1. The first comparison I want you to make is between 3/8 and 5/8. Which is greater, and how do you know? It's entirely reasonable to say, when I build a tower of 5 1/8 pieces, or lay them down on the number line like you see on the screen, it's longer. It's closer to 1. It goes further. What I want students also to reason about, though, because they won't always have base 10 materials, is the idea of 3/8 represents 3 pieces, each of them 1/8 in size. 5/8 represents 5 pieces, each of them 1/8 in size. So all these pieces are the same size. In one case I have 3, in the other case I have 5. 5 of a thing is generally going to be more than 3 of a thing. So 5/8 must be the larger fraction. If a student didn't have base 10 blocks, we talked about concrete, which your building is, or representational, the idea of draw a sketch. I'm going to use my pre-drawn number line, but this could be a freehand line segment on a piece of scratch paper as well. I can create eighths. There's approximately a half and fourths. So those pieces, give or take, are 1/8. And so in the case of my first example, I have 1, 2, 3 pieces 1/8 in size. In my other example, I have 5 pieces 1/8 in size. 5/8 is going to be bigger. This is the sort of sketch a student could make even if they don't have the base 10 materials, or not the base 10, the fraction tower materials available to them. The next example I'm going to give you uses similar reasoning, but you don't have fraction tower pieces to explore this one with. I've used fractions where we don't have fraction tower examples. I want you to think in a similar kind of logic. Which is greater? How do you know? 4/7 or 4/9? Your number line is there if you'd like to draw a picture, but if you can reason about it in other ways, that's fine. These common numerator problems are interesting because our instinct as math teachers is to create a common denominator and turn it into our 3/8 and 5/8 problem like we just looked at. But let's think about how we've defined fractions. 4/7 means 4 pieces, each of them 1/7 in size. 4/9 means 4 pieces, each of them 1/9 in size. What do I know about the size of the 1/7 piece compared to the size of the 1/9 piece? I know that the 1/9 piece is smaller because I've divided my whole into 9 segments instead of just 7. So I have 4 of a bigger piece, 4 1/7 pieces, or 4 of a smaller piece, 4 1/9 pieces. Well, 4 of the bigger piece is going to be greater, so 4/7 is greater. Our third example can be solved in a couple of different ways. You can build a model if you'd like, or you can reason about it. Which is greater, 2/3 or 3/4? Take a moment to build a model, to think about what you know, and prepare your own answer. Pause if you'd like. I'm going to use my fraction tower pieces to craft a model, but I'm not going to craft the model you might expect. Let me grab a 1/3. And let me grab a 1/4. Again, always recognizing that my 0 is here and my 1 is here. So my unit, my whole, is the same. And if I want to mark the locations of 2/3 and 3/4 on my number line, I can use the two fraction tower pieces I have to do that. 2/3 is 2 of the 3 1/3 pieces it takes to make 1. So this point right here represents 2/3. It is 1/3 away from 1. This mark here represents 3 of the 1/4 pieces, 3 of the 4 1/4 pieces that it takes to get to 1. The fourth 1/4 piece is here, so this is 3/4. Each of these fractions is 1 unit fraction away from a whole. And because 1/3 is bigger than 1/4, 2/3 is further from 1 whole and therefore smaller, or 3/4 is closer to 1 whole and therefore greater. This is another way students can reason about fractions. I'm using simple, straightforward examples. I encourage you to do the same so that it's easy for students to think about this. You might want to rewind and listen to the explanation for a second time because it's not the way we tend to think of fractions. But when you look at what research says about how to teach fractions effectively, these strategies of really building on the size of unit fractions and using those to help us compare and reason about fractions is very important. So we want to think about that. The last example I have for you, again, is one that cannot be modeled, but it builds on the idea of benchmark fractions, of using a fractional reference point to compare fractions. So which is greater? Explain why or how you know. 11/20 or 13/28. Take a moment, pause if you'd like, and think about which is greater. While 20ths and 28ths are not particularly friendly fractions, I was kind in the sense that both denominators are even. So it's very easy to identify what is 1/2. 1/2 of 20/20ths would be 10/20ths. 1/2 of 28/28ths would be 14/28ths. And so if I know that, I can say, well, 11/20ths is a little more than 1/2, 1/20th more than 1/2. 13/28ths is a little less than 1/2, 1/28th less than 1/2. So it must be that 11/20ths is greater because it's the one whose value is slightly more than 1/2, and that's going to be larger than something whose value is slightly less than 1/2. And that kind of reasoning about fractions when asked to compare them is a powerful tool for students to think about one whole. Are there any fractions in the set that are larger than 1? Well, by default, those are going to be bigger than those that are less than 1. Are there fractions that are between 1/2 and 1? I don't need to convert them to a decimal. I can reason about them to figure that out. Are there fractions that are between 0 and 1/2? And use different strategies. So you've seen here 4 different strategies. Working with benchmarks, looking at how far fractions are from 1, looking at common numerators, and looking at common denominators, all of which allow students to compare fractions while reasoning about their size and not just doing computation of one sort or another in order to figure out what's happening. I'm going to switch gears now from reasoning about fractions to thinking about fraction operations. And the example I've chosen for our webinar today is dividing a fraction by a fraction. What can we do? How can we help a student understand why fraction by fraction division behaves as it does? Many of your students may come to you with the misconception that division always makes things smaller. And then we give them a problem like 2 divided by 1/2 equals 4, and the answer got bigger. And they're very confused. That's the misconception that I'm trying to break, trying to change with the example I'm giving you, and showing how students can reason about and understand what's going on as they work with fractions. So I'm going to make an analogy to whole number division. If I have a problem like 10 divided by 2 equals what? What that's asking me is how many groups of 2 are there in 10? If I have a set of 10 counters and I start pulling them out 2 at a time to fill cups or bags or something, how many of those groups can I make? That basic logic applies, that translation of a division sentence applies even when I'm working with fractions. So I'm going to start here with naked numbers. 1/2 divided by 1/3. How many 1/3s are there in 1/2? I might, as a real-world example, say I'm making cookies, and each batch of cookies requires 1/3 of a cup of milk. I have a 1/2 a cup of milk. How many batches of cookies can I make? So how many of these 1/3 cups of milk, because that's a batch of cookies, can I get out of my 1/2 cup of milk total? I'd like you to take a moment now and think about how would you use your fraction tower pieces, How would you use your fraction tower pieces to model this problem of 1/2 divided by 1/3? In particular, I want you to reason about how big the answer is. Is the answer less than 1? Is the answer about 1? Is the answer more than 1? A little more than 1? A lot more than 1? Don't worry about a number. Just reason. How many of these orange 1/3 pieces are there in this pink 1/2 piece? There's at least one, right? Because I can see that. If I draw, just come along the length of this 1/2 piece, I get to the end of the 1/3 and there's more half left. So there's at least one. If I grab a second 1/3 piece, there aren't two. So by reasoning, my answer is somewhere between 1 and 2. And that's going to allow me to check my work later when I come up with an answer. The question is, what's this? What's the piece that fills that spot? Can you take a moment with your fraction tower pieces? Feel free to hit pause on the recording while you work on this and figure out what fraction tower piece fills in that gap between the length of the 1/3 piece and the length of the 1/2 piece. After some trial and error, you'll discover that it's the teal piece. And you notice I've rotated it to the blank side because I really don't want to think about its label of 1/6. I just want to know it's this teal piece that fills in the gap, and you'll see why in just a second. So I could say to how many 1/3s are there in 1/2, that there's one 1/3 and one teal piece. But I really want to think about what fraction of another third does that teal piece represent? Oh, sorry. What fraction of this orange 1/3 piece does the teal represent? You can figure that out if you need to by making a tower out of teal pieces that is the same height as the orange piece. And if 2 teals makes 1 orange, then 1 teal must be half of 1 orange. So 1/2 divided by 1/3. How many 1/3s are there in 1/2? There's 1 whole 1/3, and there's another half of a 1/3. Not worried about algorithms. Not thinking about what's the rule right now. Just reasoning what's going on here. How many 1/3 pieces are there in 1/2? Visually, I can see it's more than 1, less than 2. So I have to figure out how much more than 1, and I do that by identifying the teal as filling in the gap. Pink equals orange plus teal, and teal is 1/2 of another 1/3 piece. So my answer is 1 1/2. I can make 1 1/2 batches of cookies. Let me share a second example with you. This one I'll present on the screen as a word problem. How many 3/4 cup servings are there in 2/3 of a cup of yogurt? So what this tells me is that these 3 1/4 pieces, 3/4 of a cup, is 1 serving of yogurt. I have 2/3 of a cup. Is that more than 1 serving, less than 1 serving, about 1 serving? I can use a similar sort of logic here to figure out the problem. It's less than 1. How much less than 1? Well, it turns out that black pieces make a lovely tower. And so if I take these and build a tower that's the same height, it will end up taking 8 blacks to make this orange. And it will end up taking 9 blacks to make the 3/4. So this orange is 8/9 of a serving. I don't expect students to solve every division of fraction problem this way, but I want them to think about this and be able to reason about this so that as they work with division of fractions, they can quickly and mentally say, what does this mean? Is my answer going to be less than 1, more than 1, about 1? And then use invert and multiply to get an answer, but use that common sense understanding, that conceptual understanding, to check that answer and say, does this make sense? That's how we build the connection. between conceptual understanding. This is what division of fraction means. How many of this piece can I get out of that piece? How many of these can I get out of those? And this is the algorithm that we use, the procedure that we follow to get an answer. We need to see how those two relate to one another. I'm going to switch back to the PowerPoint. And if you'd like for this one, simply watch me. You've been doing a lot of doing. I'm going to move to the place value chips now. If you want to pause and get your chips out, you can, but if you'd like to just watch this one, that's okay too. Place value chips, as I said, are little counters or tokens, each labeled with a place value. And the set you have represents all of the places from hundred thousands to 100ths. So you can see 8 different places between hundred thousands and hundredths in this set. And these represent a non-proportional model. Think about what we did with base 10 materials. To scale up to hundred thousands, the pieces would be huge. Using a proportional model is really not helpful. But these can still be used to act out in a manipulative way what's happening, in decimal computation. So I've started a model here and I've color-coded things. I'm adding 2 and 31 hundredths to 13 and 46 hundredths. And so not only do I have my problem written where the decimal point is aligned, you can see that on the right, but I've also built a model for 13 and 46 hundredths already. 110 for that one in the tens place, 3 ones, 4 1/10th pieces, and 6 100th pieces. The first step in my addition problem is going to be to build my model for 2 and 31 hundredths. There's my 2, there's 3/10ths, there's 1/100th. In order to add, just like I did when I learned to add whole numbers, I simply pull the groups together. 2 ones and 3 more ones makes 5 ones. 110 and no more tens makes 110. Don't freak out on me. I know I'm doing these out of order, but listen to my language. I'm following what I know about place value. 3/10ths and 4/10ths make 7/10ths. 100th and 6 more hundredths make 7 hundredths. And I have to add that decimal in to make sure that those values stay what I want them to be. One of the ways you can make adding and subtracting decimals, particularly addition of decimals, different for students in this Foundations course is have them think about adding and subtracting in terms of place value, like I just modeled here. I don't always have to work from left to right or right to left, as long as I know what the values are. It's a little more complicated when you need to regroup. But this is really how most of us as adults do quick mathematics when we're adding a long column of numbers. Most of us start actually on the left with the largest number. How many thousands do we have? Now let me add hundreds and I'll increase my number of thousands as I need to as I regroup. Now let me add tens, let me add ones, let me add decimals, and work in that way. This is simply a strategy for modeling that and thinking about regrouping. So the place value chips are used to model addition and subtraction with whole numbers and with decimals. They can also be used in a grouping model for division. Remember my 10 divided by 2? If I have 10 ones, how many groups of 2 ones can I make? I could take those 10 1 counters, 10 blues, and form groups of 2 and think about what's going on there. So those are your place value chips. I want to move now into connecting arithmetic and algebra. And how do we help students think about what's going on in arithmetic and how does that inform what they'll be learning about in algebra? Remember, you can always use your pause button to organize material. Here we're going to be working with base 10 blocks and the factor track. and we're going to be working with Algeblocks on the quadrant mat. We'll be using the base 10 materials first. And I want to switch very quickly to my document camera. Actually, let me show you what we're going to be doing first. I'm first going to model 12 times 14 with base 10 blocks, because I suspect your students are not fluent with whole number multiplication. And I want to share some new strategies that you can use to help them become more fluent. I'm also going to show you the connection between 12 times 14 and x plus 2 times x plus 4 with the Algeblocks, thinking in both cases about where the distributive property happens and how this really represents the meaning of multiplication. And then we'll end with x minus 2 times x plus 4, what happens when negative terms come into play. So in this case, I'm going to switch first to my document camera. And you can see what I want you to build in with your base 10 materials. This is my base 10 factor track, just a giant plastic L. And you can see I've taken a rod and 4 units to make 14 on this horizontal axis. And I've taken the rod and 2 single units to make 12 on my vertical axis. I'm going to switch gears now back to my virtual manipulatives because I think it's a little less distracting than the lovely patterns of the sunshine on my mat right now. But since my image looks a little bit different, I wanted you to see first what you would have here. So now, here you can see my representation of 12 times 14. Most of us would approach this problem like this. 4 times 2 is 8, 4 times 1 is 4, 1 times 2 is 2, got to put down the 0 and move over, 1 times 1 is 1, add it all up, I get 168. 168 is the answer, but there's no mathematical understanding whatsoever reflected in the way I solve that problem. So I want to show you a model using our base 10 materials. I'm using the red lines to separate factor and product. You have your factor track, but on the virtuals, this is the way it works. And I'm going to think about what piece do I have that fills in this area that represents the product of 10 times 10. 10 times 10 is 100, and you can use your flat to fill that in. 10 times 2 is 20. This is an instance of the distributive property because I'm multiplying 10 times 10 plus 2. 10 times 10 is 100. 10 times 2 is 20. 4 times 10, this part of the area, is 40. And you can use your base 10 materials to fill in there. And 4 times 2 is 8. With your base 10 blocks, go ahead and pack things in tightly. I find on my screen it's easier to see what we have if I leave these gaps. But you can see that this represents 168, and it represents the area of a rectangle that is 12 units on one side and 14 units on the other. Perhaps that's how many square feet of carpet I need for a 12 by 14 foot bedroom. That's one example of a real-world context I might include. I don't want children to always have to carry around base 10 materials with them, however. So I want to teach students how to sketch, how to draw a representation of what they've multiplied here. And to do that, I typically use a small square to represent my flat, line segments to represent my rods, and dots to represent my units. And so you can see here, I'll sketch it freehand. If I didn't have base 10 material, you've taught students this strategy and you're now sending multiplication problems home, but you don't have enough base 10 material to send home with them. So my problem is 10, 11, 12 times 10, 11, 12, 13, 14. I am going to use the luxury of 2 colors 10 times 10 is 100. 10, 20, 30, 40, 50, 60. And if I'm confident and I don't want to draw all the dots, I can just write an 8 there. If I'm not sure, let's say it was 27 times 38. I'm not sure if 7 times 8 is 56 or 63 or 54 or which one of those. I could draw all the dots. Let's look at another representation of this. Makes it a little more abstract, but still shows the distributive property quite nicely. Here, 10 plus 2 times 10 plus 4, just what you have built with your base 10 materials. And each cell in this Punnett square, or this array model, can be filled in with the relevant product. 10 times 10 is 100. 10 times 2 is 20. 10 times 4 is 40. 2 times 4 is 8. Add all those up, 168. The power of this model is twofold. One, I can sketch it on the back of a napkin. And two, it works no matter how big my numbers are, because it's simply expanded notation and the distributive property. That leads me to this same multiplication problem, but now using a strategy called partial products, where I'm not going to lie, because there were some lies in the first model I shared with you. Unintentional, but lies nonetheless. 4 times 2 really is 8, but that was never 4 times 1, it's 4 times 10, and that's 40. It was never 1 times 2, it's 10 times 2, and that's 20. 10 times 10 is 100. Add them all up and I get 168. When students work through this cycle, they're working through concrete to representational to abstract. I could add my Punnett square model right in here somewhere. I want students to know these different representations and have experience with them, because one or the other will make sense. And then they can come to understand the other approaches as they relate to the one that makes the most sense for them. Take a moment now, pause if you need to, and I want you to put your base 10 materials away and take out your Algeblocks. You'll need the quadrant mat that you can see on the screen. You'll need your set of your factor track, your axes. You'll need yellow rods. You'll need some yellow flats, and you'll need green units. Feel free to pause while you get things organized and start the recording again when your mat looks like mine. The problem I have here represents x plus 2 times x plus 4. I know it's multiplication because I'm thinking about area, what fills in this rectangle. And in the case of the quadrant mat, where now I might have negative numbers involved or negative terms involved, each axis represents one factor. So this whole y-axis, vertical axis, represents x plus 2. And because they're all positive, they're all up at the positive end of that axis. This whole x-axis, horizontal axis, represents x plus 4. And again, because they're all positive, they're all off to the right. Remember, we have a negatives example coming up in just a moment, but right now I want to stick with positives because this is going to be quite similar to what we just did with 12 times 14. I suspect your students, like many, when you ask them what is x times x, they give you the very predictable and very frustrating answer to us as algebra teachers that x times x is 2x. Look at this in light of what we've been talking about with the area model. Visually, does that make sense? Can you find a piece in your set of yellow X materials that makes more sense to represent the product of x times x? It's not 2x, so I'm going to get those two pieces out of the way. And I hope as you look, you'll find x squared. and see that it fits quite nicely. For many students, this is the first time they understand why we call an exponent a power of 2 squared, because it creates a square as a shape. But I'm using my distributive property. X times x is this piece called x squared. X times 2 is 2x's. X times 4 is 4 more x's. Get it moved over where it needs to be. And then 2 times 4, I'm going to take these en masse, gives me 8. So now you can physically lift your factor track out of the way. I have to slide. Whoops, I did that wrong. I have to slide my pieces out of the way because I don't have a virtual factor track. But you can use your factor track to simply lift the factors out of the way and look at the product. And what do you see? You see x squared plus 6x plus 8. Pardon my messy mouse writing. If x has a value of 10, that expression shows me 12 times 14 equals 168. The multiplication process is exactly the same. Feel free to pause and rewind. Take a look again if I'm moving too fast. What I'm showing here is that even when I have yellow rods that represent x, and the orange rod, the darker orange, like I have here, will represent y. We're not going to do one of those examples. But the same idea. I can use my variables to represent the two factors, x plus 2 times x plus 4, and then build the area model in exactly the same way I did for base 10 materials. Now, the other question I promised to address here is the relationship about what if a term is negative. So this is a very similar problem, but I have x minus 2 as my first factor, and you can see that because x is here in the positive part of the factor track and 2 is down here in the negative part. I'm still building this area rectangle. So x times x is x squared. X times 4 will give me 4x. This part is exactly the same as what we did the first time. I'm just using my distributive property. Each part times each other part. Now, x times negative 2, these guys are going to come down here and fill in this part of my rectangle. But it's still 2x's. They're just down in a negative part of the mat. And then negative 2 times 4 will give me negative 8. Here's where it's especially important to use your factor track to remove the factors from the problem, because you can see how easy it would be to include did it wrong again, to include the factors in the solution, and that's not helpful. So let me get those out of the way. And now my product is x squared plus 4x minus 2x minus 8. And I know those last two terms are negative because they happen here in the negative part of the mat. I also know that I have some zero pairs. There's an x and a negative x. That's a zero pair. There's an x and a negative x. That's a zero pair. So my simplified answer is x squared plus 2x minus 8. Pardon my messy mouse writing, but I wanted you to see things as we talk them through. Negative terms mean that there's a little more cleaning up to do. There's some more details to follow, like simplifying to remove zero pairs, like simplifying a fraction perhaps. But the fundamental mathematics is exactly the same. And one of the things that I hope you see me doing here is I'm slow to simplify. I'm not worried too much about simplifying fractions. I'm not combining like terms too quickly, because I find when I do that too fast, it makes the mathematics look like magic. There's too much to be done. And I don't want there to be the students to have to jump their thinking like that. I want to see the math and make it obvious, even if that means an extra step, even if that means not quite as elegant an answer or a procedure. There's time for that elegance and simplification later. I went one too far. Let's come back to the PowerPoint. And we paused at this point in the live broadcast of the webinar for questions. Feel free to email my emails at the very beginning of the presentation if you'd like to ask any questions at this point. It's also a good time to take a break. We're a little more than halfway through our content. The next module of the course that we're going to think about is the idea of proportional reasoning. And how do we help students understand ratios and proportions? I'm going to ask you to use your Cuisenaire rods. So if you didn't already while you were taking a break, go ahead and press pause, put away your Algeblocks, your base 10 materials, and get your Cuisenaire rods out. And once you have your workspace cleaned up, here's the problem I want you to think about representing, or the statement that I want you to model in mathematical terms. The highway department can paint lines on 1 mile of road in 2 hours. And my challenge to you is to press pause and use your Cuisenaire rods. You can also use number lines, tables, graphs, other kinds of tools to create as many different models as you can for this situation, and be able to talk about how you know each model is equivalent to that stated ratio. So again, your challenge question is that the highway department can paint lines on 1 mile of road in 2 hours. Use your Cuisenaire rod, use other tools that you can sketch. Go ahead and pause the webinar and make as many models as you can. And then when you're ready to explore some of these possibilities and their implications, continue with the webinar, and I'll share some of my representations with you and talk about why those are important examples. The sunlight has changed while I've been broadcasting, so I'm going to have to adjust a little bit of where I place things to make it minimize the impact of the sun on what you see. The highway department can paint lines on 1 mile of road in 2 hours. I'm going to choose to use my orange Cuisenaire rod to represent 1 mile of road. And if I do that, then 2 yellows might represent 2 hours. Is that a model you found? Did you find others with the Cuisenaire rods? You might have used dark green to represent 1 mile of road. And 2 light greens then represent 2 hours. Or 1 red to represent 1 mile of road. And then 2 whites represent 1 hour. Let's say that I wanted to think about the answer to the question, how many miles of road could I paint if I worked for 4 hours? So 4 hours, I'm going to use red and white because it's small and it's easy. 4 hours is represented by 4 whites. That means 2 reds or 2 miles of road. What if I worked for 6 hours? 6 whites. 3 miles of road. And I can talk about how I know all of these models are equivalent because this one chunk of rate is represented by 1 single rod, that's my 1 mile, and 2 smaller rods that together add up to that, representing 2 hours. Those 2 hours need to be the same because it is 2 1-hour chunks of time, 2 of the same unit. You might have represented some of this with a chart where you looked at the number of miles and you looked at the number of hours. And students can think about these charts in a couple of different ways. They can think, okay, as I move from 1 mile to 2 miles, I'm adding 1. And as I move from 2 hours to 4 hours, I'm adding 2. There's the 1 mile in 2 hours of my ratio. They might also think multiplicatively. If I want to go from 1 mile to 4 miles, I multiply by 4. And that means multiplying my number of hours also by 4. So there are 2 ways to approach this. There's an additive approach. 1 mile plus 1 more mile gives me 2. 2 hours plus 2 more hours gives me 4. Or there's a multiplicative way. How many copies of this? This is times 3. I made 3 copies of that model. And I want to look at that. I could also use a double number line, which might resemble a tape diagram or a bar model. This is the double number line from your fraction set. I've added a couple of extra marks here, 1 here and 1 here, just to give me a few more options. This represents 1 mile, and going that same distance, that takes me 2 hours. Second mile, now I'm at 4 hours total. So I can use a bar model, a tape diagram, or something like that in my work. Sorry, I didn't go to the right spot. Here on my virtual manipulative, you can see I've used the XY coordinate pegboard. Feel free to watch for this example. I'm going to give you an opportunity to take the pegboard out and graph with it in a little while. But for right now, you're welcome to just look. It's the same chart I had before. Number of hours, number of miles. And this time I've plotted the points. You can see that I chose to put hours on the x-axis because traditionally that's where we graph time. And so the number of miles is on the y-axis. And you can see that I've drawn what I call slope triangles here, where if I wanted to calculate the slope for this line, obviously now I'm moving into the idea of linear functions and proportional relationships more than a simple ratio. I need to understand that the idea of slope is based on the idea that these three triangles I've drawn are similar triangles. And so in order to do that, we're going to look at another manipulative tool. We're going to look at your AngLegs tool. So once again, pause, put your Cuisenaire rods away, and get out your AngLegs. You're particularly going to want blue and red and purple. And I'm going to create some space here. While you clear your materials. And get myself all set up before I switch back to the camera. So we're still thinking about this problem, but now we're thinking particularly about these slope triangles and the idea that similar triangles are proportional. That definition of similarity that is so precise to mathematics. It's not about almost alike or kind of the same, the way we use similar in casual conversation. It's about they have a proportional relationship. So I can use my AngLegs to build a slope triangle by snapping them together using the buttons at the end. And as I do that, you'll see that I can create a right triangle. And if you imagine this laid on my graph, the red represents the line that connects 2 points on my graph. Purple represents rise, blue represents run. That was my first triangle, which went 1 unit each way. If I want to make a triangle that's twice as big, it's going to be 1 more red unit on the diagonal, 1 more blue unit on its length. And how tall is that height going to be? My horizontal is 2 blues, my diagonal 2 reds, so my vertical will be 2 purples. This triangle is twice as big as the one I started with. My single size model, right here, 1 of each. My double size when I consider the whole thing. So if I come back to my active inspire diagram, my original single represents this purple triangle. My double, the green. You could pause if you'd like and go on and make this triple, the orange, and see that those triangles are all proportional because each one is a scale multiple of the one before it. AngLegs are a terrific tool for lots of geometric ideas, but in this course and this context, we're particularly using them to think about slope and the fact that because any of these triangles in a line are proportional, they are similar to one another, I can always calculate the slope no matter which 2 points I choose to calculate from. So we've talked about modeling equivalent ratios with Cuisenaire rods. We've used AngLegs, and you watched me with the pegboard to build similar triangles and use that as a tool for understanding slope. I want to move next to equations and inequalities. As always, take a moment to pause and organize your materials as you follow along. We'll be working with Algeblocks, particularly the yellow X rods and the green units, and we'll be using the sentence mat this time, and you can see what that looks like on my screen. So feel free to pause for a moment and get your materials together. And I'm going to switch back to Active Inspire, and we'll look at these two examples of solving equations step by step using the Algeblocks. Here's the sentence mat, and I have our first equation, x. Did I go 2 pages? I did. I have our first equation, x minus 4 equals 3, set up here. Let's take a look at the mat and understand what we've done. I have the equal sign in the middle and a balance beneath it to remind students that the equal sign is about two expressions that have the same value, that even each other out in weight on the mat. My left-hand expression is x minus 4. So just as we did with the quadrant mat, x is positive, it's up in the positive part of the mat. Negative 4, so the 4 is down in the negative zone. Equals, on the other side of the equal sign, I have a simple positive 3. One of the challenges is for students to think about, how do I solve a problem like this? And why do I follow the steps that I follow? Algeblocks can help us because we can talk about the variable x as having a preference for being alone. Our mathematical phrase is that we want to isolate the variable. But really it's that x is terribly antisocial and doesn't want to make any friends. The other thing that's important to remember is this balance has to stay balanced. So everything I do as I solve an equation is in service of those two goals: keep the equation balanced and help x be by himself. So if I want to get rid of this negative 4, it needs to go away. The way I know how to do that is by creating zero pairs. So negative 1 plus positive 1, that's a zero pair. Negative 1 plus positive 1, that's a zero pair. That's a zero pair. I've made these zero pairs, but what's happening to my balance here? It's tilting dangerously because I've only added positive 4 to the left. I also need to add positive 4 to the right. And the way we record that is we say add 4 over here. And that's the same as the 4 that I'm adding on this side. And I do that because 4 and negative 4 are additive inverses. And so that allows me to say that all of this is one big fancy complicated way of marking 0. So I'm going to drag those off the mat because they're zero pairs and I want to get them out of the way. And so success on the left-hand side now, all I have is x. And over on the right-hand side, I have 7. So x equals 7. Students can see how each action they take on the mat has a mathematical correspondent to work with it. And they can work on naming the properties and understanding the rules and principles behind the steps that they take and why they work. Our second example is x plus 2 equals 5. I could use my additive inverse strategy again and add a -2 to both sides. That's the strategy that always works, and that's why I modeled it first. But here, because my green units are both in the positive part of the mat, some here and some here, I have another strategy available to me. That is, I can subtract +1 from both sides. And in fact, I can do that twice. So I can subtract a +2. And on the other side, I also subtracted a +2. And when I put all that together, I'm left with x plus a +2 minus a +2, that's plain x, equals 5 subtract a +2, +5 subtract a +2, +3. And I don't need to write the +3 because it's our convention that represents a +3. So this strategy of take some off of both sides of the mat, the thing you have to be careful about is that only applies when it's in the same part of both sides of the mat. Let me go back here and reset this. X minus 4 equals 3. I can't take 4 off from the left and 4 off from the right because they're not both in the negative part. They're not both in the positive part. So my only strategy here is to add the inverse, add a +4 to both sides. That's why I like to teach that model first, and then later we can go to the special case here where I can subtract 2 from both sides. I can also still, because it'll always work, add -2 on the left. Take quick advantage of digital world, add -2 on the right. So there's some 0 pairs. Here's some more 0 pairs. X equals +3. I can subtract a +2 or I can add a -2. Those are inverse operations and they get me the same result in both cases. And that's how I can begin to use the mat for the Algeblocks, the sentence mat on the Algeblocks, to explain step by step how I solve equations. To work on graphing in 4 quadrants, now we are going to use your XY coordinate pegboard. So if you haven't already done so, take a moment to pause, clean up your workspace, and then take out your pegboard. You'll want to snap the axes on the pegboard and go ahead and take some pegs and some bands out of your box, out of the envelopes that they come in. I'm going to switch back to my camera so that you can see my pegboard. I've used blue pegs to indicate the origin, and then I counted out 5 in each direction on this board, both to anchor my axes. These blue pegs do not represent points I'm plotting, but simply to anchor my axes and to give me a reference point for counting. That's 5. So if I need to find 3, I can quickly count 2 down. Or if I need to find 6, I can go back to 5 and quickly count 1 up. It gives me that tool. Our problem was this, y equals 2x plus 1. And the first thing I'm going to do is complete this table of values. So if x is negative 3, that means 2 times negative 3 is negative 6, plus 1, my y value is negative 5. If x is negative 1, you can go ahead and pause or fast forward if you don't want to listen to me work all of these. In fact, I won't work them all out loud. Negative 2 and 1 is negative 1. Now I'm going to use red pegs, my other color, to plot the actual points that I've found. So my first point is negative 3, negative 5. So on my x-axis, I'm going to go left 3 and down 5. Remember, my blue peg serves as a reference. Negative 1, negative 1. 0, 1 on that y-axis. 1, 3. And 3, 7. I can then use a red geoband to mark my line. And I can begin to think about not only the points I've plotted, but the attributes of this graph. The different items that I can know about it and remember about it. What kind of function is this? If I move ahead to our function study, what are the key features of this function? Can I talk about domain and range? Can I talk about slope? Can I talk about intercepts? How can I represent those things on the pegboard and using this tool? That's the move to functions that is the last part of your course, where again, I'm creating a table of values, but now I'm thinking about it in function terms. F of x is negative 2x minus 1 in this case. And you could create a table of values and make a graph in exactly the same way that we did for the other. So here, get rid of my old graph. I'm actually going to rotate this because I noticed as I worked, the axes are labeled with a small x and a y. I had put mine down rotated the first time, so I fixed it now. If I put in negative 2 times negative 2 is 4 minus 1 is 3. Input and output, just like before. Plot my points. Feel free to pause the recording if I'm going too fast. You may want to make your own graph. Again, questions to consider. What kind of function is this? What are the key features of the function? I can think about domain and range. I can think about slope and intercepts. Remember, I'll reuse this blue peg. That defines my slope triangle. If I come down here, rise, and over here, run. I can think about intercepts. This one is at a point on the y-axis. That's simple. This one I'm going to have to estimate or do some calculations to find because it's not at an even point. And that points out one of the important things to remember working with the pegboard. That is that it is not amenable to graphs of any number you might want. You're going to want to be strategic in your choice of functions and expressions that you use and range that you use. Notice that the axes are mobile. If I take out these pins or you take out the pins, you can slide them. So if you need to work only in one quadrant, that's not a problem. But that's the last tool that you have. Again, if you have any questions, feel free to reach out to the folks in your district or to me directly. We're happy to help you get those questions answered. I so appreciate your spending time today in this webinar and exploring these materials. I hope you've been hands-on and using your own materials as you've worked through this. It gives you a feeling for what this will be like for your students and does the best job of preparing you to work with these materials in your own classroom. Thanks again and have a wonderful school year.